Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we're going to be doing Unit number 4, Lesson number 3 on quantifying the steepness of a curve. This is one of my favorite lessons and it's going to require the use of a graphing calculator pretty extensively. So make sure that you have that out and are ready to go. Because today we start exploring the most fundamental question of calculus, which is how do we assign a number for how steep a curve is at a single point along that curve. But first, let's talk about lines again. Exercise 1. How do we quantify the steepness of a line? What number, just to make sure everybody understands it, when we say quantify something, what we really mean is assign a number to it. That's, I guess, a really loose definition of quantifying. Assign a number to it. What number do we use to quantify the steepness of a line? Well, hopefully it's pretty obvious. We use the slope of the line. Now notice we talk about the slope, right? Now I know for years you've heard that, all right, well, all lines have just, one slope. Okay, it doesn't matter which two x values you pick. You might even think that a couple lessons ago we even proved that when we showed that the function f of x equals a times x plus b has a constant average rate of change, delta y to delta x equals a. But of course that was based on the fact that we sort of assume that that's the equation of a line, right? You might say, that's not an assumption. My teacher's been telling me that for a long time. But let's get away from an equation or anything else. Let's make sure that we understand from a very basic point of view why it is that the slope of a line is the slope of a line, right? So there's a line, and I'm going to do a couple things. I'm going to mark some points off on it. This, and let's say this one. I'm going to actually put a couple of them up here and here, all right? My claim is it doesn't matter whether we find delta y divided by delta x for these 2 points or delta y divided by delta x for these 2 points, it's going to be the same. And now let's make sure we understand why. The reason why is if I start taking lines and drawing in parallel lines, I'm really hoping these things end up looking pretty parallel. Yeah, they could be worse. Actually, not much worse than that last one. So let's say that these are all parallel lines, right? But maybe they're all parallel to the x-axis. Let me throw that in. Right, then what happens is that I can say that this angle and this angle, well, I can say that they're equal. Now, if I were to drop in a little altitude here, make that a right triangle, and drop in a little altitude, make that a right triangle, well, now by default, this angle must be equal to this angle. Think about that for a minute. But that means that this triangle, the one right here, and this triangle, the one right here, those two triangles are similar because they have all the same angles. Right? One of them is just a blown up version of the other one. But one thing that you should have learned about similar triangles or similar figures in other courses is that the ratio of corresponding sides is always equal. So in other words, if I took, let's say, delta x here and delta y here, and I divided them, delta y divided by delta x, I would get the same thing as if I took delta x and delta y here, different ones obviously, and I divided them, right? But that is, by definition, the slope. That's the slope. Right? So the slope of the line being the slope, not just one of the slopes, is based on that similar triangle argument. It doesn't matter how close, how far away, or what 2 points we use on the line. Any 2 points that we use when we draw in this right triangle, it's going to be similar to any other 2 points, and therefore the change in the height versus the change in the base, right? Those two divided will always give us the same number, the slope. All right? That's kind of cool. Let's take a look at number 2. Number 2 says, given the parabola below with points A, B, C, and D marked, list the points from the least steep to the most steep. All right. Now this is going to seem kind of silly, and I'm sure that most of you will be just fine at it. But in other words, if you were climbing up this, let's say, parabola, clearly not linear. Let's say you're climbing up this parabola. At what point would the hill be the steepest? At what point would it be the least steep? Should be easy. Pause the video now, though, to write down the order. All right. Well, I hope that everyone said B was the least steep, then D, then A, then C. So this is the least, and this is the most. Now, the reason that I wanted to lay that out there, even though it probably seems very obvious, is we all have to agree qualitatively. We all have to agree qualitatively that the different points on the parabola have different steepnesses. If you're looking at that just like you look at a line and go, yeah, well, steepness at B is the same as it is at C, or A is the same as C, or D is the same as A, then we have a problem. Then we have a serious problem. But if we can all agree that B is the least steep and that C is the most steep, then we can start to ask the question, how do we quantify that steepness? With a line, it's easy, because any 2 points we pick, we can just find the slope between those 2 points, and we can say, that's the slope of the line. That's it. But how do we quantify the steepness of a curve whose steepness is always changing? Oh, that's tricky. So far, the best we've done is talked about average steepness, or average slope, or average rate of change. Now we want to talk about what's the steepness right there at point A, or right there at point B. All right, pause the video now, though, and write down anything you need to, and then we'll erase the text and go on. All right. So let's investigate the simplest nonlinear curve we can, y equals x squared. All right, make sure to have your calculator out at this time. In exercises 3, 4, and 5, I'm going to walk you through a procedure, but I'm only going to do it once because it's kind of hard to do it in these presentations. On the other ones, I'm just going to have you be doing it on your own and then give you the answers, all right? But what I want to do is I want to look at the classic, right? We all know this thing, f of x equals x squared. And I want to take a look at something that's very curious as we put this thing underneath the microscope and zoom closer and closer into the point 1, 1. Just be comfortable, right? 1, 1 lies on this parabola, right? If I put 1 in for x, I get 1 out for y. All right? So let's bring out the TI-84 Plus. All right. Now that the calculator's out, it is going to have to cover up some of exercise 4 just by default, but that's okay. You don't need to look at it right away. What I'd like to do is I'd like to first take a look at this curve under the standard zoom window. So let's just put it in. All right, let's go into y equals. Clear out any equations you might have there. And I'm going to put x squared in. All right, very simple function, shouldn't take us much time. All right, and now what I'm going to do is I'm going to do a standard zooming window. In other words, I'm going to go from -10 to 10 in the x and -10 to 10 in the y. I can do that by just hitting the zoom button, the one that's up here. And then I go down to zoom standard and hit enter. All right, and I see my classic parabola. All right, and right around there, right, is the point 1, 1. I think I just got an email on my phone, but I have the point 1, 1. But what now I'd like to do is I'd like to zoom in on that point. I'd like to get closer and closer and closer. And our calculator actually has a zoom in feature. Now I use zoom in conjunction with another feature called the value feature. So I want to zoom in on the point 1, 1, and I'm going to show you how to do that now. What I'd like to do is go into the calculate menu, right? It's right up here above the trace menu. Okay, so let's go into calculate. And let's just choose option 1. It's called value. So let's just hit enter on option 1. We're back out to the graph, and notice how it's asking what x equals. So I'm just going to type in 1. X is equal to 1, and I'm going to hit enter. Now really what value is for is to tell us what y is when we know what x is. But what I'm using it to do is to put the cursor on the point 1, 1. That's the only reason I did that. So hopefully right now you're looking at the same parabola in the standard viewing window, but the cursor is now at the point 1, 1. So now what we're going to do is use the zoom in feature. So what I'd like you to do now is hit the zoom button, And we're going to go down to option 2, zoom in. All right? And I'm going to hit enter. Now notice the cursor has drifted a little way from 1, 1. That's completely okay. Don't move the buttons. Just hit enter to zoom in. All right. So the graph doesn't look all that remarkable. It's like, okay, well now we're looking at a smaller picture of it, but we can still tell pretty much that it's y equals x squared, right? And it looks like that. So what I'm going to do is I'm going to zoom in a couple more times because I want to look at this graph really close to the point 1, 1. So let's go through that procedure again. I'm going to go back to value. So I'm going to go above the trace button, go back to value. I'm going to choose option 1. I'm going to put in x equals 1. All right. Tells me y is equal to 1. Again, just to put the cursor at 1, 1. Now I'm going to go into my zoom options. I'm going to go down to option 2, and I'm going to zoom in. All right. Now, this is weird. If I showed you the first graph we ever looked at today, all of you would probably say that's a parabola. If I showed you the second graph that we looked at today, the last zoom, you'd say, it's a parabola. If I show you this graph, you start to think, maybe this is a line. Maybe this isn't a parabola, right? If I gave you this graph on a test, no other graph, and I said, what's that the graph of? Would you really pick a parabola? I think you'd probably pick a line. Now, you know it's a parabola because you know what its equation is. You know it's not a line. But let's zoom in one more time. So I'm going to go back into the calculate menu. I'm going to go down to value, right? I'm going to put x equals 1 in, just to put the cursor at 1, 1. That's all. That's the only reason. Now I'm going to hit zoom, and I'm going to go in. Enter. Now, I don't care who you are. I don't care how smart you are. I don't care how observant you are. If I put the graph that's now on the screen on a test, and I say, you've got two choices. This is a line, or this is a parabola. No tricky things here. Which one is it? I would assume 100 out of 100 people would tell me that it's a line. All right? But it's not a line. It's a parabola. And yet, if we go in close enough, what we will always find on a smooth curve, what does smooth mean? We'll talk about that more as time goes on. But on a smooth curve, what we'll find is if we zoom enough on any point, it will eventually look like a line. That is a property known as local linearity. Local linearity. In other words, very local to a point. Any function that's smooth acts linear. It acts linear. That's amazing. I don't care if it's x cubed, square root of x, sine of x, cosine of x, tangent, secant, cosecant, e to the x, ln of x. I don't care. You zoom in enough at a point, it's going to start acting like a line. All right? So let's take a look at exercise 4. Now, don't worry about what it says there. You know, at the end of the day, I love this phrase. If it looks like a duck, it swims like a duck, and it quacks like a duck, it's probably a duck. So I'm looking at something that looks like a line and behaves like a line. I'm going to treat it like a line, and I'm going to figure out its slope. So that's what we're going to be headed towards in number 4. We're going to come up with the slope of the line that we see sitting on the screen right now. Now the way that we have to do that is just come up with 2 points that are on the line. Okay, now what I want is, here I've got this point at 1, 1. What I really want is I want a point that's somewhere to the right of 1, 1 and somewhere to the left of 1, 1, right? I want something like this. So let me show you how I'm going to do this. I'm going to use that value command again, okay? And what I'm going to do is I'm going to go to value, right, under calculate, and I'm going to choose value, and I'm going to put in x equals 1, again, just to put the cursor at 1, 1. But now I'm going to use the trace command, right up here. I'm going to hit trace, and I'm just going to start going to the right. All right, I'm just going to go to the right. How many times do you have to go to the right, Mr. Weiler? That's up to you. That's up to you. We're not going to get an exact answer here. I mean, we're going to get an answer, but it's not going to be the exactly correct one. So I'm going to go to the right for a ways, and I'm just going to write down that amazingly sloppy coordinate point. According to my eyes, it looks like 1.023911 and 1.048337. All right, so that's the point up here. Now I also want a point that's on the other side of 1, 1. Okay, so I'm going to go back into my calculate menu to get my value menu. Let's do that. All right. And now I'm going to go down to value, grab value. I'm going to put x equals 1 in, just to put the cursor at 1, 1. And now I'm going to hit the trace button again. All right, so now I've hit the trace button. And now let me start to go to the left. All right, I think that's probably enough. Again, we just want some points that are on either side of it. A little bit farther away is good, but I'm going to go with 0.9765625. Don't round these. All right, it'll really throw off your answer. 0.9536743. 1. All right. Now, by the way, notice how very, very small delta x and delta y are between these 2 points. They're very, very small. They're not 0, but they're both about 3/100ths, so they're small. So now what I'm going to do is the very painful calculation of slope here. I am going to do it all at once, though, so I'm going to do that y2, 1.048337 minus y1, 0.9536743, all divided by x2, which is 1.023911, divided by x1, 0.9765625. All right, I just wrote it down, but now let me type it into my calculator, okay? So, good use of parentheses here, and you can do it all at once. It takes a little while, though. 1.048337, 0.9536743, 1.023911. And long, messy decimals, they're terrible. All right, once it's in there, once I've got it all typed in, then I can hit enter. All right, and after doing a little bit of looking at this and letting it go in, I find that line has a slope of 2.000472877. So that is the slope of the line that I see sitting in there. So if I go back into graph right now, let me do it. All right, now I've got that line with a slope that is just about 2. Actually, the exact slope will be 2, but we won't be able to prove that for a couple days now. All right, so the slope of that is 2. Now keep in mind what I've really done. I haven't really found the slope of a line. What I've found is the average rate of change for very small delta x. That's what I've figured out. Very small delta x. All right? Now, obviously, I'm going to have to clear out the screen now before we go on to the next page. So hopefully you've understood what's going on so far. But pause the video now if you need to. Then I'm going to clear out the screen. All right. Now what you might not have a sense for is what we're even getting at. Don't worry. We're getting there. We'll get there. Let's take a look at 5. It says form the equation of the line that would pass through the point 1, 1 with the slope you found in exercise number 4. Then graph this line along with y equals x squared using the standard viewing window. How would you describe the line compared to y equals x squared? Sketch below. All right, well, let's not worry about the calculator for right now. Let's assume that the slope was exactly 2. We could use the 2.0004, that would be fine, but I'm gonna use this. So I've got a slope and I've got a point, right? So we can form the point slope form of a line, y minus 1 equals 2 times x minus 1. Now keep in mind that what I want to do is I want to graph this thing along with the parabola. In order to graph it, I have to have it in y equals form. So I'm going to write it as y equals 2 times x minus 1 plus 1. All right, so let's put that now into our calculator. All right, and see what it looks like in the graph. So let's hit y equals. Obviously, in y1, we still have x squared. In y2, I'm going to put in 2 parentheses, x minus 1, parentheses, plus 1. If you want to turn that into y equals mx plus b form, you certainly can, but you don't have to. All right, that's in. My parabola's in. Now what I want to do is I want to look at it in the standard viewing window. So that's just zoom standard. So let's go up to the zoom. And now let's go zoom standard. All right. Well, I think that you can probably see what's going on here. It's not the greatest window. There's a lot of stuff on there that we don't really need, all that negative y value stuff. Let's change the window a little bit. Let's go back into our window. Let's set our x minimum to be -1. Our x maximum to be, 3. Let's set our y minimum to be -1. And let's set our y maximum to be 3. Now let's take a look. Now we'll have a better sense. So let's hit graph. That I can see and interpret much better. So how would you describe the line compared to y equals x squared? And then we'll sketch it for a little bit. What word would you use? Pause the video now if you need to think about this. All right. I hope you remember. Whoops, stray mark there. I would say that the line is tangent to the curve. The line is tangent to the curve. It just glances it, right? So if I were to sketch this thing, not the most complicated sketch, I don't want that, but we've got this nice parabola coming up, and then we have the point 1, 1, and then we've got this tangent line. Will I actually be able to do it? Yeah, it could have been worse. It's not so bad, right? It's a line that just touches the curve, just touches it. Now, let's talk about this a little bit before we get rid of this, because this is important. In fact, this is it. This is the whole thing. This is how we're going to quantify the steepness of the curve. You see, at any given point on the curve, whether it's up here or whether it's down here, there's one and only one tangent line. All right? So, in other words, if I drew the tangent line here, it would look like that. If I drew the tangent line here, it would look something like that. And notice what's happening is that the steeper the curve is, the steeper the tangent line is. In fact, we are now going to define the steepness of the curve as the slope of the tangent line to the curve at that point. All right, and that's cool. And it's really based on this idea, a couple different ideas, that number one, right, when we zoom really far in, a curve looks linear. Because it looks linear, it's got a slope, right? That slope, well, we'll have methods for finding it exactly eventually. Right now, we're just finding it by zooming in, zooming in, zooming in, zooming in, and then, taking some points on either side of our target point. But the steeper that curve is, the steeper the tangent line will be, and therefore, we can quantify that steepness with the slope of the tangent line. All right? Anyway, copy down what you need to here, and then I'm going to get rid of it, and I'm going to make the calculator a bit smaller, but I'm not going to get rid of it entirely, okay? All right, here we go. Let's make the calculator a little smaller. We'll bring it back when we need it. All right, bye-bye. Okay, let's summarize all of this. This is so important. 3 important facts about smooth curves. Now, let's clarify smooth curves at this point. Hey, that was weird. Let's clarify smooth curves at this point. This curve is smooth. This curve is not smooth. This curve is not smooth. All right? So we're talking about smooth curves, things like this. All curves will look like lines under increased magnification. In other words, if I took any portion of this curve I circled it, and then you know how they draw those diagrams where they blow it up, right? What I would see is something that looks like a line, right? That's called local linearity. At any particular point on a smooth curve, let's say we took this point, at any particular point on a smooth curve, there exists only one tangent line that can be drawn. Now that's important. Only one. That's really important, you see. And here's how you want to think about it. Let's say that you had a board that you were lying up along the curve here. See, some people say, no, I think there could be more than one tangent line. But the plain fact is if there's more than one tangent line, it's got to have a different slope. So if you start rotating that board, what would happen, right, if you started to rotate this board along the curve, is that the point of tangency would change, right? It would rotate and it would suddenly be sitting like here. Now, by the way, think about why that doesn't work with a not smooth curve. If I had a tangent line here and I started to rotate it, it would just hang out at that point. But not on a smooth curve. No, on a smooth curve, as you start to rotate that tangent line, the point of tangency moves to a different point. Finally, and most importantly, we will measure / quantify the slope of a curve at a point by using the slope of the tangent line at that point. So in other words, if I came up to this curve right here, and I drew a tangent line and I figured out for some reason the slope there was 5, I would say the slope of the curve at that point was 5. Now again, it's weird because we always think about slope as being change in y over change in x, and at a single point there is no change in y, there is no change in x. But if there's a tangent line at a single point, well then we can think about the slope of that line, right? Wow, there's a lot of pictures on that screen. Pause the video now and really think about what we've talked about. All right, I'm going to clear out the text. Still haven't brought the calculator back, but we will in a bit. All right, so just a little practice with this. Practice with this, practice with finding tangent lines, seeing what they look like. The overall technique that we're doing today is not terribly important. Let me just get that out there right away. It's not terribly important. It does give you a sense for this local linearity. It does give you a way of approximating the slope of the tangent line, because you're really not finding a tangent line, you're really finding a secant line, but it's just for a very, very small delta x and delta y. All right, but what we want to do is now figure it out when x is 3. So what I'd like you to do is pause the video, take as much time as you need. It probably should take you around 5 minutes. Come up with the slope of the tangent line and its equation, so the equation of the tangent line. And then we'll also graph it along with y equals x squared. So take a little bit of time, okay? All right, well, let's talk about it. If you've done the procedure right, no matter how messy your numbers are, you should be getting a slope that's right around 6. Now, how close is close enough? Well, I'd say if you were anywhere between, let's say, 5.5 to 6.5, you're probably okay. You're probably okay. I'm going to use 6. Now, I need to write the equation of the tangent line. I have a slope, 6. I need a point. Well, I know the x-coordinate's 3. And of course, the function itself gives me the y-coordinate, which is 9. So now I have the equation y minus 9 equals 6 times x minus 3. Again, getting ready to just graph it, I'd have 6 times x minus 3 plus 9. That would be, in theory, the equation of my tangent line. Now let's look at what it looks like. Let's make the calculator big again. That wasn't very loud, but it looks like the calculator worked just fine. Let's go into y equals. We already have y squared in for y1. What I want to do is get rid of y2 now. Although it might make sense to keep it in there, but I think I'll get rid of it. And let's put in 6 times x minus 3, parentheses, plus 9. All right, probably our window is not the best at this point, so maybe what I'll do is I'll set my window. What would be the best window to set it at right now? Let's see, what did I have before? Here we go. Let's go into our window. Let's make x min -5. let's make x max positive 5. And y min, let's go with negative 5 as well. I'm going to make y max a bit bigger. I'm going to go up to 20. All right. Now let's hit graph. All right. Now there's your tangent line. That is definitely a tangent line. Real quick, let me just show you something. Because, you could botch this. It could be bad. One of the things people might do is they might accidentally do change in x divided by change in y. That would mean that the slope would be around 1/6 instead of 6. Let me show you what would happen if you do that. Let's go back into y equals. All right. Let's just do a little insert. So instead of 6 there, we've got a 1 divided by. Just insert that, so it's a 1/6. And now take a look. Enter. Oh, no. That is definitely not a tangent line. Definitely not. One more error. Let's look at one more error. Another thing that people do occasionally is they'll do y2 minus y1 divided by x1 minus x2. So they'll flip-flop the order in the numerator and denominator. What that'll always do is give you the right magnitude, the right absolute value of slope, but you'll get the wrong sign. So that would make a slope of -6. Let's take a look at that. So going to y equals, I got to get rid of that 1 divided by business. Now I just have to put in an insert and put in a negative. All right, so now I have a -6, no subtraction there, negative. All right, and graph. Ooh, again, definitely not a tangent line, definitely not a tangent line, right? Tangent lines will come up and just graze the curve and then go on their way. Sorry, that's the bell. Don't worry, I'm not going anywhere, but the hallways might get a little bit loud. All right, I want to do another one, so pause the video, all right, and then let's do another. All right, I'm clearing out the text. Let's do one with the square root. All right. Consider the curve y equals root x. Find the approximate slope of the tangent line to the curve at x equals 4 and its equation. Graph its equation along with y equals root x. Use a graphing window of, so there you go. There we just have the graphing window. All right, well, what I'd like you to do is pause the video. You got to put a whole new function in there, so get rid of your y equals x squared. But pause the video, put in y equals root x, do your zooming into x equals 4, zoom as many times as you need, don't get caught up in the method. Zoom as many times as you need to then think that it looks like it's linear, get that local linearity going on. Then do your tracing, come up with 2 points, do a little delta y divided by delta x, etc., and come up with a slope. Then come up with the equation of the tangent line, then we'll do some graphing. All right, so pause the video now. All right, and we're back. Well, you will have gotten relatively the right answer if you got a slope that was around 0.25 or 1/4. Again, I would say anything from 0.2 to 0.3, you're fine. Outside of that realm, it's a little problematic. So we've got the slope. What do we use as our x1, y1? Well, x1 is 4. y1 is the square root of 4, which is 2. So we're going to force this line to go through the 0.42. So that's going to be y minus 2 equals 0.25 times x minus 4. So just swinging that 2 over. Here's the equation of our tangent line. Let's graph it. All right, so I'm going to go into y equals. I'm going to clear out my x squared, clear out my linear. So in y1, I'm going to put in the square root of x. In y2, I'm going to put in 0.25, parentheses, x minus 4, parentheses, plus 2. All right. Now I want to graph it. I gave you the perfect window, so let's go in and use that window. Let's hit our window button. We're going to put x min in as 0. X max is 10. Y min is 0. Y max is 3. Okay. Everything's set. Make sure your window looks good. Let's hit graph. Oh, man. I love that. It's so neat. I love on this calculator that we've got the original curve in blue and then the tangent line in red. It just really makes it pop. And look at that. Definitely a tangent line, right? The line's just going along, grazing it. So now if somebody said, well, what's the slope of y equals the square root of x when x is 4? Your answer would be 0.25, 1/4, right? And it's really remarkable, again, to be able to say the slope at a single value of x is blank, is the following. And again, for us, in this case, it's 1/4, or 0.25. All right, let's go through and do one last one, okay? So pause the video now if you need to, and then I'm going to clear this out. All right, here it goes. Last one. All right, consider the curve y equals 1 over x. Find the approximate slope of the tangent line to the curve at the point x equals 1/2 and its equation. Graph its equation along with 1 over x. Use a graphing window, blah, blah. So same deal, same deal. You know, zoom in, etc., try to get it linear, all that. Pause the video now and work on it. All right, let's talk about it. Now this slope is actually our largest slope of the day, and what you should have found is a slope that was approximately -4. Again, how close? I don't know, -3.5 to -4.5, but this is the exact slope, all right? We know that x1 is 1/2, y1 will be 1 divided by x, when x is 1/2, and that's going to be 2. So we're going to have y minus 2 equals -4 times x minus 1/2. Rearranging it into a more useful form, -4 times x minus 1/2 plus 2. All right, so let's take a look. Let's see what that looks like. Let's hit y equals. In y1, I'm going to put 1 divided by x. In y2, once it's all cleared out, I'm going to put in -4 times x minus 1 divided by 2, parentheses, plus 2. All right, make sure that all looks good. Let's go into the window now. We want x min to be 0. We want x max to be 1. We want y0 to be 0. We want y max to be 10. All right, and once it's all set, let's hit graph. Isn't that cool too, right? Nice graph. Again, really kind of cool. You can now say right here at this point, on the parabola, right, what we've got, not on the parabola, sorry, it's actually a hyperbola, but on the curve 1 over x, right at the point x equals 1/2, that thing has a slope of -4. So the slope of the tangent line and the slope of the curve are going to be defined as being equal, okay? It's just the way we're going to quantify the steepness of a curve, is by the steepness of the tangent line that could be drawn at that point on the curve. All right, we'll pause the video now, write down anything you need to, and then we're going to wrap it up. Okay, here it goes. I think we can finally let the calculator rest. I think it's done its job for today. All right, it's gone. And let's finish up the lesson. So today we started confronting one of the greatest questions in mathematics. How do you take a curve whose slope is always changing and quantify how steep it is at a point, given that to calculate steepness, to calculate slope, you need to find the change in x divided by the change in y, right? And yet here we're talking about a single point where there is no change in x, there is no change in y. And what we saw was that if we zoomed in close enough, that curve would look like a line, and we could pull 2 points off that curve, calculate the average rate of change, and call that the slope of the tangent line at that point, which then is also the slope of the curve at that point. All right, well, that's it for now. I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kurt Weiler, and until next time, keep thinking and keep solving problems.